This is our CV3 dev kit, and what we're showing here is a multi-camera perception demo. So we have 6 8-megapixel cameras all running in parallel, and 4 3-megapixel cameras that are aimed back at us. And you can see down here all the perception results being displayed. So each one of those cameras is running 3 networks, 3 neural networks. And altogether, even though we're processing all those things in parallel, we're using about 25% of the CV3 performance.
Well, I'm actually surprised that you have a fan on there because
it's
50
CV3.
watts. I don't know.
Well, first of all, we want to make sure there's no issue, but
okay.
Our main goal here is to demonstrate that you can have a super powerful domain controller that doesn't need water cooling.
Yeah.
Right? Because that's the thing that really drives cost up.
And what is the, because I can't remember the specs, when we talk about all the sensor fusion the CV3 can do, how many cameras, what's the maximum number of cameras, maximum number of radar, what's the maximum number of sensors it can handle?
Total of 24.
Okay, and it doesn't matter if they're radar or image.
Right. That's right.
And if somebody wanted to do LiDAR down the line, that could be one of the sensors as well.
And LiDAR can also come in over Ethernet, so
okay.
It doesn't need to use those.
Okay, great.
Okay. So speaking of radar, we're also demonstrating here CV3-based centralized radar processing. Mm-hmm. So that's one of our differentiations, is that we can take raw radar data coming in, and using our Oculi technology, even with a relatively small number of antennas, you can get very high definition radar and very large number of points coming out. So this is a scene where we're capturing, you can see the shape of those objects as they move through there, and the resolution is actually very similar to LiDAR resolution.
I've seen that scene before. Quick question about it.
Yeah.
Is there a kind of a minimum resolution on the radar or radar quality? I don't know what the actual rating is on the radar sensors, but is there kind of like a base minimum that you want people to use?
So you can see here we have actually 3 different types of radar modules, which is basically just scaling up the number of antennas. So this is a single MMIC chip, which is a 3x4 antenna array. This one is 2 MMIC chips, so 6x8, and this is 4 MMIC chips.
So those say Ambarella. So are you actually assembling?
These are prototype modules
prototypes,
that we do just for customer evaluation.
Okay.
And so, in terms of automotive applications, we think this is the sweet spot in terms of high definition, because you can get to like 0.5 degree angular resolution, and you can see the form factor is easier to integrate than the 4-minute version.
Yeah. Cool. Great. Thank you.
This demo is showing our...
Probably better if they look through the peak hole first.
Oh, okay, yeah. If you want to take a look on the side here, you can see this is a extremely low light. You won't be able to see any. You won't see it because it's too...
Actually, it's coming up. Okay.
Okay, so that shows you what a typical image pipeline can see. And with our image pipeline, standard image pipeline, you can see more detail there, but you can see like things that are moving.
Very grainy.
It's grainy and it's blurry, right?
So that's what's inside that dark room right
exactly.
now. But but the imaging can still pick it up, so that's great for night.
That's
now,
impressive.
when you apply our neural network-based image pipeline, you can see we can get a significant improvement in quality even relative to our standard image pipeline.
And what's the light meter reading, Don?
0.2 for lux. 0.2 lux.
Wow.
Yeah. So that scene, it's very difficult even for human eye to be
Yeah.
able to see that.
But you can see the difference in the pixels.
Well, it also shows the value of the post-processing because obviously the sensor can only do so much.
Right, and this is actually a very low-cost sensor, right? High-volume sensor, so it's not relying on the sensor to get that level.
That's great.
I noticed they selected a GT500 for
Yeah.
the car. Yeah, I was just wondering about that. You know, we took the demo ride, and I'm thinking,
Meet the
Ferrari?
Okay.
That's about half.
So this demo is showing some other aspects of what CV3 processing can do. So on the top left side is a stereo depth map. So you can see when you move closer or farther away from the camera, the color is changing because the depth is changing.
Oh, wow. And blue. So green.
And then on the right side is optical flow, which is detecting motion. So when I move my hand, you can see it's picking up with the motion, and we can actually tell what direction as well as how fast it's moving. And those are very useful for providing kinds of redundant information to the neural networks to detect objects when it's not something it's seen before.
So what's the value of the kind of the outline on the bottom left?
It's a cool looking demo.
That's what I think. It is really cool looking.
Yeah, it's just showing that we can do classical computer vision algorithms as well as AI-based algorithms. And the bottom right side is showing a visualization that's generated by the built-in GPU that we have in the chip. So that's something that people use typically for surround view. Right. In theory, I think this thing it should be.
So you use a GPU.
Rotate it.
I was going to ask about that if
Yeah.
you can rotate it,
Yeah.
because that's I
Yeah.
think the next level of
Right, that's right.
top view cameras that you do.
Did Ambarella develop the GPU, or is that a licensed
No, that's
IP?
a licensed IP.
Okay.
And it's just for visualization purposes.
So like an ARM Molly or something like that, probably.
It's a imagination.
Imagination. Okay.
Okay.
Are your processors in the CV3 ARM or RISC-V or?
The main high-level processing is ARM A78s. Okay. And this demo here is showing a combination of front camera ADAS and driver monitoring, both running at the same time on our CV2FS front camera chips.
So it's recognizing you as the driver.
Yeah. I think like you can see it's eye gaze, that kind of stuff. So it's provides a very cost-effective solution for a module that's mounted on the windshield.
Yeah.
And over here,
So basically, the CV3, so you're doing not just the ADAS solution, but you're also doing some of the in-car solutions, like the driver monitoring on the
So-
same
That
chip
wasn't,
or not?
That wasn't CV3, right?
right,
Okay.
that one is running on our CV2
Okay.
FS chip, but in the future, we could also run that same software on the CV3 along with all the rest of the camera suite.
Yeah. So do you envision the CV3 to also be able to eventually drive certain functions within the digital cockpit, whether it's maybe a heads-up, excuse me, heads-up display, some kind of or something within the dash to give you the recognition information that you need that's gathering?
Potentially, but I think in many cases it's going to be handled by an integration between the CV3 and the infotainment system.
Okay.
So, obviously we can send information over to the infotainment system.
Okay.
So this is a partnership demo that we're showing between Applied Intuition, which is a company that has developed a very extensive software simulator for autonomous driving development. And what we've done is integrate their simulator with our hardware so that you can run hardware in the loop simulation. So what that means is I can create a scenario, and here you can see the input to the simulator, which is like a high definition map of the road that I want to use, along with various other cars that I want to have driving. And the simulator will generate a virtual world around that, which has buildings, trees, and all these cars behaving the way I specified. And then all these images will get fed into, in this case, the CV5 chip. And then the CV5 chip will run the perception, and perception results are displayed here. And it will also, in this case, run adaptive cruise control. So it's doing basic lane keeping and showing like when the car gets too close, it slows down, and when it gets farther away, the car is going to speed up again. So this allows you to test the full stack, autonomous driving stack, in a virtual environment without having to have any real sensors and stuff.
Yeah, that's better than having consumers test it for you.
Exactly.
In real life.
You're right. You can obviously test much more dangerous scenarios than you would want to test on the
And the
road.
CV5 is available now.
Yeah. So this is actually a prototype, but we will be introducing a CV3 PCIe card that can plug into your servers, so that you can scale up the amount of simulation that you're going to do without having to build many real sensor suites.
Okay.
So this is something that's many of our automotive customers, CV3 customers, have been asking for a way to do the low-cost simulation and high performance.
That's great.
I think that one's available now.
Okay.
Oh wait, they just jumped in it.
You want to pause?
Well, they want to hear about more than just automotive.
Yeah, so we can take a look over here at another demo. This is another CV3 demo showing a robotic, simple robot here, which has stereo cameras in the front and back and lateral cameras on the side. And what it's doing is basically targeting these stop signs that we have, and also detecting obstacles, right? So if it detects an obstacle, it stops. Otherwise, it drives towards the stop sign. And when it gets too close to a stop sign, it's going to stop and then turn 90 degrees. So that way it can navigate through this scene. So this could represent like a typical warehouse environment where you want to drive around.
Now, I believe last year you introduced at CES the CV5, correct?
Yes.
No, that was the CB3.
Oh, that's right.
No,
That's 1 year old.
No. I
It
am
was the
talking
year
about.
prior we announced
Oh, okay.
CB5.
Yeah.
So, I mean, obviously everything is focused right now on the CV3. When do you think we get to? When is CV5 needed?
Well, CV5 is really targeted more for AIoT applications.
Okay.
So security cameras, other kinds of.
Okay, that was my misunderstanding. So thank you.
You're welcome. We went out of order in the numbering, so that might
I
have
know.
thrown you
Very
off.
confusing.
It did.
The numbering system is kind of skewed.
It is a bit, yeah.
That's why we don't let engineers do marketing.
But marketing is the one that picks the numbers. This is another kind of smart warehouse application where we're demonstrating a fence, a safety fence. And you can see here we have a stereo camera up there, which is detecting where people are relative to this fence. And basically it can detect when somebody is moving inside this and then trigger an alarm, right? And if you just put your hand in there, it will detect that, but it won't.
Can you shoot up lasers so we can keep people in? I'm just kidding.
And that's the sensor up there.
Yeah, and you can see it's basically knows where people are relative to it.
So I have to ask you, obviously you guys are working on IoT applications and automotive applications. How much technology transfer is there between the two, especially in terms of all the software stacks and training and learning and everything else?
Well, at the core technology level, there's quite a bit of commonality.
Yeah.
So things like the CV flow processors that we develop, we have different versions for higher performance, lower performance, but we can basically scale the same core architecture for all those things. Same thing with image processing and so on. But automotive has a lot of safety requirements. It requires special hardware on top of the standard technology. And same thing on the software side, you have to add more stuff to meet the safety requirements.
So is the IoT the base that you build upon, or is it the automotive that you strip stuff out to get
I would
IoT?
say the automotive kind of is right now needs more performance at the high end, so that drives some of the technology development. But once we have that, it's very easy for us to derive, and you will see us derive AIoT solutions from the CV3 family platform.
Now you're doing for the IoT stuff, you're doing mostly image sensors here, but do you see an application for radar in this type of environment too?
Yes, I think so, because again, things that are like robotics, definitely people are very interested in using radar along with cameras to provide redundancy and motion information, and also in security for certain cases. Like obviously radar can see in very low light conditions.
Okay. So dark factories, great application.
Yeah. So I guess maybe we should move on to So this is another robotics demo using CV2 family chips, and you can.
Hi, we're SLAM Core. We're partners of Ambarella. We provide the SLAM solution, and Ambarella provides the chip. So we're using the CV22, and it has a camera on it, but we're using the RealSense for this current demo. For the next iteration, we will be using the camera on the chip itself. So what you're seeing now is kind of like a robot vacuum cleaner application. So what we've done is using our SLAM system, we've previously mapped this area out, so you can see on the screen the dark purple shows the map, the occupancy map that we've generated, and the cost map is in the cyan and the lighter purple. So what the cost map is it's a extra safety boundary to account for example, the radius of the robot. So what we've done now is we've added an obstacle there, and you can see that once the camera turns to it, you'll be able to see it. And so I'll try to go inside as well, and once it turns around, you'll see that it updates, and it will be able to see my silhouette as well, and it will be able to go around me. So the navigation is an open source thing. The robot base is open source as well, so we provide the SLAM, Ambarella provides the chip, and everything else is off the shelf.
Well, I just saw it moving that roll of duct tape, so is it actually programmed to be able to move objects?
No, it's not. So I think it was trying to find a path around us, and slightly moved across
I'm
it.
just thinking if you could train it to put away kids' toys and
That would be amazing for us.
everyone would be happy.
Exactly.
It needs a gripper though.
So Jim, he has to go real quick, so let's do this demo.
Thank you.
Thank you.
Okay, so this is a benchmarking demo that we're comparing the CV3 dev part against a large competitor's GPU, high-end automotive GPU part. And we're using a network which is part of the industry standard MLPerf benchmark suite, SSD Net ResNet 34. And we use exactly the same version of the network running on both chips. Here you can see the competitor chip is running at 128 frame per second, and CV3 is running at 705 frame per second, so about 5.5x improvement in performance. And even though it's much higher performance, the power efficiency is actually 4 times better, which typically when you go to higher performance chips, it's the other way around, right? Power efficiency gets worse. Also, we're showing the memory bandwidth that's used is about 10 times lower per frame. That means that you can scale up performance more and also run other functions like ARM processing and that other processing that you saw there. All those things can be running at the same time. Whereas what we see on many of our competitive chips, that when they try to put everything together, run everything at the same time, they run into the huge DRAM bottleneck.
Yeah. So, and that is the chip itself.
Yep, that's our module, CV3 module, the chip and the DRAM.
Well, what process node are you running?
5 nanometer.
Cool.
All right, thank you
you very
guys.
much. I
Yeah.
appreciate this.